Hello again, everybody, and welcome back to MTED 110. Today we're going to be doing lecture 3B. We're going to continue with chapter 3, and we should finish chapter 3 today as well. Let me go ahead and pull up the slides, and we'll begin. Okay. Oh, yeah. So remember, this is where you want to pause and make sure that you've completed activity 2B before you begin. Activity 2B was, oh, which one was that? The one with Felix's apple farm? Yeah. So now you should be very comfortable with addition and subtraction, comfortable with our numeration system. And today what we're going to talk about is we're going to talk about how to model multiplication and division. So um, let's start here. Let's think about ways of thinking about multiplication. And we're going to start with a Dora moment here. Just take a moment and ask yourself and your group members, what do these problems all have in common? And I'll just give everybody a minute to go ahead and think about that. Okay, and now I want you to speak out loud about it. Talk to yourself or talk to your neighbor, talk to your group members. Just take a few minutes to talk about it out loud. Okay, so let's take a look at some of these questions. Now, what you might have noticed right away is that they're all multiplication. They're definitely all multiplication questions, but even more than that, they're actually all the same multiplication question. Take a look at the numbers that appear, right? If one piece of candy costs 4 cents, how much would 3 pieces cost? Well, that's 3 times 4. That's computing 3 times 4 cents, which is 12. Same thing with the next question, right? The numbers are the same. 4 miles per hour for 3 hours. How far will you have walked? Well, 4 miles per hour for 3 hours, that'll give you 12 miles, right? This one is also the same problem. 4 by 3, that's 4 times 3. Hey, actually, I have this right here. There you go. 4 times 3. Remember this guy, the 2 staircases? Just like that. What's the area of the rug? And then same with the last one. Maya has 4 blouses and 3 skirts. So the thing is that these are all the same multiplication problem, but they're all given in different contexts. And what we want to do is we want to be able to model these different contexts in an edifying way, meaning a way that'll give students a nice foundation for what's going on. Yeah, so how can we model these things? Well, let's take a look. So the first model is this, and you can always, always, always go back to this, and I'll say always a lot in this particular lecture, but you can always think of multiplication as repeated addition. That is kind of the definition of multiplication. It's basically repeatedly adding something over and over and over again. That's what multiplication is. So if one piece of candy costs 4 cents and you want to know how much 3 pieces would cost, you count 4 cents 3 times. You say 4 cents plus 4 cents plus 4 cents gives you 12 cents. That's just repeatedly adding, and that's multiplication. Same thing here. If Jackie walks at 4 miles per hour for 3 hours, it's doing 4 plus 4 plus 4, and you get 12 miles. So once again, it's just repeated addition. So in general, when you have a whole number n of quantities, each with value q, and they're combined, the resulting quantity is this. And this is the symbol that we use. So basically what we're saying is that if you have n times q, what it's saying is that you add q to itself n times. So this is the exact same structure that we have up here if you look at these two examples, right? And then what we're saying here is that this is actually equal to 3 times 4, and this is equal to 3 times 4. So if there were only 3 of these things down here, then these would say 3 times 4. These would each be 4. So it's the same idea. So I want you to keep that in mind from now and on for forever, basically, that multiplication is repeated addition, all right? And this is called the repeated addition representation of multiplication. There you go. Incidentally, this is kind of cool. This is why we actually use the word times when we talk about multiplication, because we're saying add something this many times. So when we say 3 times 4, it really means add 4 3 times. 3 times 4, it's 4 3 times. So that's why we use that word times. Here's how you can model, excuse me. model multiplication on the number line, you basically just show how many times you're repeatedly adding that quantity. Or I should go this way, huh? Right? So here, we're adding 4 3 times. So this is 4 times 3 or 3 times 4. We're just going like this, and then like this, and then like this. And at each step, you're adding 4, right? To get yourself to 12. 3 times 4 is 12. And 4 times 3 is 12, which we're actually going to talk about in a second. That's commutativity. Um, yeah, so one issue that is this, access to only the repeated addition representation of multiplication can lead to misunderstanding. It also doesn't give students quite a robust enough outlook on multiplication itself. So we want to give them more models of multiplication, and we're going to see those here. This one is actually one of my favorites, the area model, and I know I've got it in here somewhere. But again, multiplication can always be represented as an area. So notice that this model works a lot better for that question about the rug, where it says a rug measures 4 feet by 3 feet. What's the area of the rug? Essentially, you're looking for the area of this 3 by 4 rectangle, right? And we know that it's going to be 12 because we know that 4 times 3 is equal to 12. But the point here is that we can model that. And pictorially, you can see the quantity 12 right here. Each one of these little cubes, there's 12 of them, right? So if you do 3 by 4, then you end up with 12 units, 12 unit cubes, all right? So that's the idea right there. Let me ask you this. Where in the figure can you see 3 plus 3 plus 3 plus 3? Just take a moment and think about it. Do you see it? You see 3 plus 3 plus 3 plus 3? I can see it right here. Here's one group of 3, and then another group of 3, and then another group of 3, and then another group of 3. And lo and behold, you're just adding 3 4 times. That's what's going on. That's multiplication for you, right? Can you see the 4 plus 4 plus 4? I think now you can probably see it here, right? Here's 4 plus 4 plus 4. So we can connect the area model to the model of repeated addition. So this is exactly what we want to give our students. We want to give them this ability to flow between these different models, give them these different really, really helpful representations of this operation multiplication. That's what it's all about. And I'll say this a bunch, and I really, really, really want you to carry this with you forever too. Multiplication can always be represented as an area. Always, always, always. Anytime anybody ever says something like this times this or this many times, you can draw that as a picture, a rectangular picture, in fact. It can always be represented like that. So just keep that in mind, and maybe that'll help you if you're struggling with some other multiplication problem. I'm actually excited because in chapter 4, I believe, I should say chapter 4, I believe, I think we're going to talk about algorithms. We'll get to algorithms in a later chapter, addition algorithms, subtraction algorithms, multiplication algorithms, and division algorithms. But let's stay here. And then there's another representation of multiplication called the fundamental counting principle. So that one basically says this: if there are m ways of doing something and n ways of doing something else, then there are m times n ways of doing both things. So again, take a moment and maybe pause here and think about what that's saying. But it's saying if you've got m ways, like maybe you had 3 ways of doing one thing, and then 4 ways of doing another thing, then there are 3 times 4 ways of doing both things, right? It doesn't seem too confusing when you say it like that. But this is where, oh yeah, so this scenario. Maya has 4 blouses and 3 skirts. So you probably thought about this yourself, right? Like when you're looking through your closet and you're trying to pick out an outfit and you're like, okay, well, if I pick this blouse, then only these skirts will go with it. And so it starts to like narrow down your choices, but you have all these options to begin with, right? And so the question is, how many options did you begin with? Well, if you've got 4 blouses and 3 skirts, you're going to have 12 different outfits to choose from. And in the past, you've probably seen this modeled using a tree like this, a tree. Let me see if I can zoom in so you can get a closer look at this one. There we go. A little bit. Let me do this. Come on, I'm trying to get that last little leg in there. Anyway, the idea is this. You start out And in this particular example, Maya has 4 choices of blouse, right? Blouse 1, blouse 2, blouse 3, and blouse 4 down there. And once she makes that choice, she then has to choose one of the skirts. And she has 3 skirts to choose from. So she could wear blouse 1 and then choose skirt 1, or wear blouse 1 and choose skirt 2, or wear blouse 1 and choose skirt 3. So that's 3 different outfits right there. And then she can do that for every single blouse. And what you'll notice here is that she ends up having exactly 12 choices of an outfit, 12 possible results of an outfit. And that's called the fundamental counting principle. That's the fundamental counting principle. Okay. All right, so some definitions. Again, I'm not, actually, there are a couple definitions in here that you do really do need to memorize. In particular, this one. Uh, you should know what a factor is. And we're going to have this discussion later on in chapter 11, actually, which gets pulled forward a bit. But if you have a product written like this above, these 2 numbers here, we refer to those as factors of the product. Those are A and B are factors of the product. And the result of multiplying those 2 factors together is the product. And so that's what C is over here. C is called the product. So I hope that makes sense. C is like the result of a multiplication, or I should say a product is the result of a multiplication. And the things that are being multiplied are all called factors. They have some other special names here too that we're going to talk about. C can also be referred to as a multiple of A or a multiple of B. That's basically saying if you, I'll say it this way, if you take A and you repeatedly add it B times, then you get C. So in other words, C is a multiple of A, but you could do the same thing for B, and you could say C is a multiple of B. And if that doesn't make sense, please ask more questions and I will be happy to clarify it. Some other interesting definitions here. The first factor, A, is sometimes called the multiplier, the thing that's doing the multiplying, kind of. But uh, I don't really like that term that much because numbers are not the things that are acting. Numbers are not causing the action. The operation of multiplication is the action. So I hate to call a number a multiplier because it's not like a number is really doing anything. It's just a thing, right? But sometimes this first factor is called the multiplier, and sometimes the second factor is called the multiplicand. Did I say that right? Multiplicand. I don't even know how to say it, so you can imagine how often I use it, right? Generally, we just call these things factors. So if there's one definition that I want you to take away from this, it's that A and B are called factors. All right? Okay. Oh yeah, a non-zero factor can also be referred to as a divisor. Let me see here. So basically, either of these factors, if they're not zero, they could also be called divisors. And we're going to focus on those definitions more in chapter 11. So you'll have another chance to refresh your memory in chapter 11 about those things. Okay, first off, the commutative property for multiplication. Everybody loves it. Everybody knows it. It basically says that it doesn't matter which order you do the multiplication in, you'll get the same number as a result. The product is the same. So A times B is the same as B times A. That's what that means. Here's a pictorial representation of that because we want to be able to explain this concept to our students without relying on just these symbols, right? And what's cool is that with multiplication, you have the area model, which is just so perfectly geometric, right? And you can use this to show all of these properties. So the commutative property of multiplication literally means that if you've got this many blocks, the number of blocks doesn't change if you go like this. There you go. So I had a horizontally oriented rectangle, you could say, and when I rotated it, I didn't change the number of little blocks that are in there, right? That's the idea. So that's a way of showing the commutative property of multiplication. All right, next is the associative property of multiplication, and it's the same thing as it was with addition, except now it's multiplication. You can multiply these 2 first, and then multiply by a third, and that's the same as multiplying these 2 first and multiplying by that third remaining one. Wait, which way am I pointing? Right there. There you go. That third remaining one. I'll just do that. I'll just point over here. Um, so that's the idea. And there's also a very nice picture for this one. Here it is. Notice here that there are three factors, and multiplication can always be represented as an area, right? Well, that's an area, and then this is almost like another dimension. So when you multiply two numbers, you get another number, but in this case, we're going to get like one of these right here. And then you got to multiply it by another one, and that gives you this stack right here. So this is a way of showing that no matter how you slice this rectangular prism thing, the number of cubes doesn't change. That's really what it means, the number of little cubes. Let me just emphasize this a little bit here. So notice down here, this is 3 times 5 times 4. And each one of these little slabs is representing the quantity 5 times 4, which is 20, right? And the 3 is basically being counted right here, 1, 2, 3. Now, equivalently, although slightly different, right here, this is 3 times 5, okay? And then we have 4 of those sets, 1, 2, 3, 4. So that's showing you how you can multiply 3 times 5 first, and then multiply by 4, and you'll get the same result. And this is just showing you that basically all we've done is we've taken this box and stretched it out in different ways, or not even stretched it out, just like partitioned it in different ways. But even if you partition it in any way, it's not going to suddenly make more blocks appear, more unit blocks, right? Okay. Distributive property. So the distributive property lives up to its name. Oops. What do you think of when you think about distributive? Distribution, right? Distributing things, handing things out, for example. Well, that's exactly what the distributive property says. It says that you're going to distribute this factor to each of these terms right there. So if I try to do something like 2 times 4 plus 6, I can just distribute that 2 to the 4, and then I can distribute that 2 to the 6. And then I'll get the same result. So in this case, it would be what? 2 times 4 plus 2 times 6, like that. Just like that. And that's the distributive property. Here again is another pictorial representation of it. This right here is 5 times 3 plus 4. And right here you can see the 5 times 3 embedded. And then right over here is the 5 times 4. And then over here, they've got them split up. So basically, you can see that if you pushed these two pictures together, you would have this picture right over here. So it's showing you that the distributive property is actually true, that if you were to do that, you're going to get the same result. Actually, I really like this particular picture because if you'll notice, they take very great care not to abuse the equal sign. So notice here that they've got this equation running along the top. And that's the only time you actually see the equal sign and the plus sign, because they're just talking about adding those numbers and equating those two expressions. Just a nice little tidbit there. Anyway, what's next? Okay, so that's it for multiplication. We'll see algorithms in a later chapter. Now let's think about division for a moment. Let's look at these two problems, and I want you to ponder them again. Before I do a Dora moment here, let's talk about this. The first question says, suppose that you have a deck of 52 cards, and you deal out hands of 4 cards until none are left. How many hands did you deal? Or the second question, suppose you have a deck of 52 cards and you deal them out to 4 people. How many cards does each person get? Now, before we proceed, one thing I want to point out here, and this is a good time to make this a teachable moment. A standard deck of cards sometimes looks like this. Actually, let me go ahead and go back to the camera just to make this clear. So a standard deck of cards is like this one. This is a pack of bicycle trading cards. And in this deck of cards, you've got cards that look like this. Cards that are numbered, and they all have different suits. There are 4 different suits. Let me see if I can pull some out. This is a club. This is a diamond. This is a heart. And this is a spade. So those are the 4 different suits in a deck of cards, just like so. Let's see if I can hold it up. There we go. Different suits. Now, each suit, so like the hearts, has 13 cards in it. Ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, Jack, King, and Queen. So cards are very nice if you want to talk about probability and statistics and counting problems or even division problems because there are some interesting divisors of the number 52. So each deck, standard playing card deck, comes with 52 cards. There's a whole bunch of them, right? And you use them a lot in school, and you'll use them a lot in not calculus, am I thinking? Statistics classes. But the reason that I'm taking the time to actually explain this to you is because it's a good time to kind of, frankly, check your privilege, because there are some students that might have never ever seen these before. I remember one semester, I think it was a few years ago, I just started up talking about cards and 52 cards and jokers and kings and all those things. And I had a student who was like, yeah, I've never actually played with a deck of cards, so I don't know what you're talking about. And that was just a revealing moment for me where I was like, oh yeah, I had to like recognize my own bias because I've been playing with cards since I was a kid, but not everybody does. So one thing to keep in mind when you're teaching your students is you might actually have to think about what manipulatives or what resources you're using because some of your students might not be familiar with them, right? Okay, so enough of that aside. Let's go back to this. And yeah, so let's have a Dora moment here. And I want you to just ponder for a minute and think what is similar or what is different about these two problems. All right, and now go ahead and talk out loud to yourself or talk out loud to your friend or talk out loud to your group members. Okay, so now I think you can probably see that again, the math problem is the same in both of these, kind of like the example with multiplication, right? But there's a subtle difference to these ones. Oh yeah, so there you go. First, they both involve computing this quotient here. 52 divided by 4 equals 13. But the first question involves counting how many groups of 4 are in 52. So you notice here that it says you deal out hands of 4. This one is like taking the deck and going, counting 4 and then setting down that group, counting 4 more, setting down that group, counting 4 more, setting down that group. That's what the first question is. The second question is slightly different in structure. The second question involves repeatedly subtracting 4 until no cards are left. So that one's like going 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. You see what I mean? So you're repeatedly subtracting 4 until you don't have any more cards left. So it's slightly different contextually, right? All right, so some definitions. Let's look at this. If you see this mathematical sentence, it is pronounced like this. A divided by B is equal to Q. So that is how you would say that out loud in English if you saw this set of symbols right there. Some definitions. This number here, A, it is called the dividend. B is called the divisor. Oops. B is called the divisor. Should highlight these things so it's a little easier. A, dividend. There we go. B is called the divisor. And then Q is called the quotient. Q is called the quotient. So those are some good terms to know. In particular, divisor is an important one to know. Just make sure you're comfortable with it. The result of a division is called a quotient. That's another thing. So this guy right here is called the quotient. That's the result of a division. All right. When B is not a factor of Q, so in other words, if Q is not a multiple of B, right? If you can't get to Q by just adding B some number of times, or I should say some whole number of times, then that means that Q is not going to be a whole number. In other words, what I'm saying is that when you do this division, you don't always end up with a whole number over here, right? Even like 3 divided by 2, that's 1.5. That's not a, that's not a whole number, right? It's like in between two whole numbers. So anytime that B is not a factor of A, there's going to be some stuff left over. There's going to be some stuff left over. And that extra stuff is called the remainder R. So in that case, we can then write this. And we'll talk more about this in chapter 11. So if this doesn't click right away, don't worry about it. We're going to talk more about it later. Um, but this structure is going to be familiar because this is actually what pops up when you do the division algorithm. You end up with some whole number, q, and then you end up with some remainder if it doesn't divide quote unquote evenly, right? We're going to talk about not using that phrase later on too, but if it doesn't divide evenly, then you end up with a remainder, and you can write that as some little bit, some little fractional bit. Okay, there we go. All right, so now this right here, see, I really should box this particular phrase before I say this. This right here is the most important understanding of division that you can take away from this course. So this is one of those phrases that I almost want you to burn into your memory. But whenever you see this symbol, A divided by B, I want you to like knit together the sentence, how many times does B go into A? That's always what it means. So anytime you ever see something divided by something else, it literally means how many times does this guy fit inside of that guy? And what's great is that this goes the same for fractions, right? I can't remember, is it here or later that I talk about it? I think it's later. Okay, it's in a different lecture. But look at this right here. A divided by B is the same as A over B. We're going to talk about this later, but you can actually see it. That's one of the reasons they use this symbol for division, right? Because it basically shows that A goes on top and B goes on the bottom. So those two little dots are placeholders for the A and the B, or the number, right? So what I'm trying to get at here, right, let me say that again here. Here's A, it goes on top. Here's B, it goes on the bottom. That's where that symbol comes from. Anyway, anytime you see a fraction like that, I want you to say this out loud to yourself every single time. Just trust me on that. It's going to make things make a lot more sense, and it's going to provide you a lot more profundity when you talk about division. How many times does the bottom go into the top? So if I say something like, oh, let's do one like this. How about 12 divided by 3? What does that actually mean? Well, it means how many times does 3 go into 12? How many times does 3 go into 12? 4. It goes in there 4 times. And that's why that's equal to 4. That's the definition of division. There you go. That's why that's equal to 4. So if you can wrap your head around this, it's going to help you out so much. I can't even express to you how much it helps out. Okay, let me get. Oh yeah, so we can find this quantity by repeatedly subtracting the quantity B from A, right? So basically you take A and you start pulling things out of it. Right? Does this look familiar? Repeated subtraction, taking away, right? There you go. We're taking the quantity B out of this container as many times as we can. And once we know how many times that is, that's the result. That's A divided by B. That's the quotient. So, for example, if you've got a deck of 52 cards and you deal out hands of 4, 1, 2, 3, 4, 4, 4, how many hands did you deal? Well, you're basically doing this. You're subtracting 4 at every step. Minus 4, minus 4, minus 4. And then you count how many times you were able to do that. How many times were you able to do that? 13 times. So 52 divided by 4 is 13. Beautiful, right? Love it. Okay, so the other example is sharing and partitioning. This is the one where you basically like take an amount and you cut it up into uh, groups that have the same number of pieces inside. So for example, let's say Lebeg Elementary School just purchased 24 new Apple computers for its 5th grade classes. How many computers will each classroom get? Notice that this one is like fundamentally, or not really fundamentally, but conceptually different than the last one. Now you can like see 24 computers and you're going to start like partitioning that group. So this is pictorially what's going on. This is the partitioning method. Each apple here represents a computer, and we have 4 5th grade classes. So we're going to take these 24 Apple computers and we're going to basically partition them into classrooms, and we want each classroom to have the same number of computers. Exactly. And in that case, it's going to be 24 divided by 4, which is 6. So that's sharing and partitioning. Okay. There's also this model. This is called the missing factor model. Um, this example says Mr. and Miss Deckard will have to pay $6,900 a year for their daughter to go to CSULB. Translate this into a monthly payment that they can fit into their monthly budget. So they're trying to figure out how much money they have to save each month so that they'll end up with $6,900 at the end of the year to pay for that tuition, right? So this is what they're trying to do. They're trying to say 12 times what number will get us to 6,900. So if I repeatedly add 12 some number of times, I end up at 6,900. But equivalently, that's the same as computing this right here. It's asking how many times does 12 go into 6,900? And when you compute it, you get 575. So that tells them that they're going to have to save up $575 a month if they want to have $6,900 at the end of the year. Okay. Oh yeah, okay, so now we need to have a conversation about dividing by zero. This is one of my favorite conversations right here. Dividing by zero. So first question is this, and here's a Dora moment for you. Can we divide by zero? Hmm, 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 hmm. Okay, what do you think? Talk about it. What do you think? Can you divide by zero? Can you not? Maybe, I don't know. Maybe. Well, let's find out. Let's find out. It turns out that you cannot, but again, who says and why? Why not? Let's say somebody told you you can't divide by zero. Here you go. I'm going to write it down. I'm going to write it down on this official slide in this official lecture, and I'm going to say, uh, you can't divide by zero. You can't divide by zero. All right, you believe me? Great. Then let's move on. No, 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 don't ever say, yeah, don't believe me. You should always demand proof. You should always ask for proof. And we're going to prove it right now. You can't divide by zero, but can't is kind of a strong word too. We should be a little more precise. Let's be a little more precise. And what we're going to do is we're going to do a proof by contradiction. So we're going to suppose that you can divide by zero, and then we're going to derive a contradiction, which means that we're going to end up with something that's not possible. So we're going to assume that we can divide by zero, and then we're going to show that that leads to something absolutely absurd, all right? And that means that our original assumption must have been wrong. So let's suppose that you can divide by zero, and we're going to let k be any real number. So what I usually like to do is this. What's your favorite number? Any number you want. We'll save zero for a minute, but any number you want. I like the number 8 for some reason. Not sure why. I like the number 8. So 8 is a number. And if we're allowed to divide, then we can write 8 divided by 0. And 8 divided by 0 should be some number. Let's call it x. So in other words, we know this is true because we assumed that you're allowed to divide by 0, right? So now that we're allowed to divide by 0, I'm going to divide my favorite number 8 by 0, and I should get some result. Okay, now I know for a fact that if you multiply both sides of an equation by the same thing, they're still equal. So I'm going to go ahead and do that. I'm going to multiply both sides of this equation by 0. Okay? I also know for a fact that anything divided by itself is equal to 1. So I can go ahead and cancel these zeros right here. I also know for a fact that anything times 0 is 0 itself. So what I've now shown is the remarkable fact that 8 is equal to 0. Yay, isn't that just lovely? Wait a minute. Wait, hold on. Is 8 really equal to, wait, divided by 0? Did I make some mistake? Hmm. 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 Did I make some mistake? 8 is equal to 0? Hold on, what's going on here? Wait a minute. Wait a minute. No, that's right. That means that we can't divide by 0. Because if we divide by 0, then we get all sorts of crazy results like this, like 8 is equal to 0. The best thing to do here is, what's your other favorite number? Pick another number that you like, any number you want. What's that? 11. Okay, 11's a good one. Go through and replace all of these 8s by 11s. 11, 11. And now I know 11 is equal to 0 too. Great. What about zero? Zero is my favorite number. Sweet, let's do zero. Zero, zero, zero is equal to zero too. So in fact, what this shows is that any number is equal to zero. So as long as we allow division by zero, then everything is equal to zero. So everything is nothing, nothing is everything. The universe collapses in on itself and nothing exists. So would you like to divide by zero, or should we just say that you can't? It's kind of up to us. um, More specifically, we'll say this. We say that division by zero is undefined. That's why we try to be a little more careful. It's not that you can't divide by zero. It's that you can, but once you do, you throw away all mathematics and all logic. So you can either choose to not divide by zero, or you can throw away everything that we understand about science and technology to date. Uh, I know what I'll pick. Yeah, so there you go. In other words, every number is equal to zero. Everything is nothing. Oh, this little symbol right here, this little lightning bolt, that means contradiction. That's one of the mathematical symbols for contradiction. Okay, so yeah, we say zero division by zero is undefined. You can't define it in a meaningful way. If you try to define it in a meaningful way, then you get all of these crazy paradoxes and contradictions. Now that proof is a little bit too advanced for younger learners to follow, so you can use definitions of division to kind of help. I have a few here. I'm not going to spend too much time on them, but let's take a look. So recall this. A divided by B equals C is equivalent to saying B times C is equal to A. And we'll see this more actually in chapter 11 too. But let's plug in some numbers. And this is similar to what we did before, right? But it's a little more gentle, I would say. Let's say 5 divided by 0 is equal to some number. Well, then that means that 0 times C must be equal to 5. And the question is, what number C works to make that true? What number C can you think of to put in right there, where you multiply it by 0 and you get 5? That's right. There is no number C. No number C works, right? So that's a good way to explain to a child that you can't divide by 0. That's a good way to do it. But wait, a student says, hey, you said any number divided by itself is equal to 1, so that means that 0 divided by 0 is equal to 1. It must be equal to 1. How do you respond? Is that student right? Think about this. Wait, 0 divided by 0 is equal to 1. How am I going to respond? This is what it's like to be a teacher and in front of all these students in the classroom, and the little kid is looking at you and they're like, how do you respond, teacher? Tell me the truth. How do you respond? And you're like, oh, okay, well, let me think about that for a minute. But luckily, you've been through MTED 110. And so you're like, well, if 0, or you say 0 divided by 0 is equal to 1, if and only if 0 times 1 is equal to 0. But 0 divided by 0 can be equal to any number, and this will still hold true. This will still hold true. So once again, 0 divided by 0 is equal to any number. So it's not just equal to 1, it's equal to everything. So once again, division by 0 is not well defined. So we'll just stick away from it, I'll say. There you go. Undefined because we can't define it in a meaningful way. So this is a good conversation to have with your students at an early age, because students often feel like there's some kind of mystery surrounding 0, but there really isn't, and especially mystery surrounding division by 0. But you got to nip that in the bud, right? Tell them early on so that it makes sense to them. Oh yeah, there you go. That's exactly what I just said. So kind of got ahead of myself. All right, so we're just about done, but I have a few videos that we're going to watch. It'd be a good time to take a pause if you want to do an intermission. I'll have to set them up in just a second, but we're going to watch these videos and they're really cool. So when students can make sense of multiplication and division, they'll often devise their own methods for computing, and this is what's so beautiful about this type of knowledge. This is why we want students to have this type of knowledge. This is encouraged in the Common Core standards. So again, people that are saying like, why is Common Core teaching kids differently than the way I learned in the past? That's really not correct. We actually encourage students to try anything and everything, and we teach them the same thing that we taught them in the past, and we teach them new stuff that we learned more recently. We do it all. That's what Common Core says. Common Core says, don't just do it one way, do it many ways, and find one that works for you. There you go. There's no single way to do a problem, right? So yeah, and remember this, keep this in mind, and these students are going to exemplify this right here. There's a big difference between a student being able to actually multiply and divide as opposed to being able to use a particular algorithm to do so. So some students might not know some algorithms, some might be able to just figure out some algorithms really easily. The standard division algorithm might come to some students very quickly, for others it won't. There's a big difference between grinding through an algorithm and knowing how to divide and multiply. Yeah, there you go. Oftentimes students will find some algorithms easier than others, and that's totally fine. More power to them. We approve of that. We applaud that. Okay, so let's go ahead and watch some videos here. Let me get this set up. Get the first video set up. And be sure my audio is going through. Give me 1 second. Yeah, there we go. Okay, so this the first video is Jamea. She's a 5th grader, and let's see how she computes this problem right here. There we go.
I did, since 29 was close to 30, I had added 30, 20, 12 times because it's closer. I just rounded it to the nearest 10. So that was 30. I added that, I got 360. I had to take away 12 because I had put one more to 29 to get to 30. So I had to take 12 away. And I took that away, and I got 348.
Whoa, did you follow all that? Let's watch that one again. That was kind of fast. She was computing 29 times 12, but like our students did in some of the previous videos, the first thing she did was like, I'm not going to do 29, let's do 30. And she did 30 times 12. Let's take a look at that again, and let's see if we can kind of trace what she was doing here. 1 second. Okay, take it away, Jamea. Try that again.
I did, since 29 was close to 30, I had added 30, 20, 12 times because it's closer. I just rounded it to the nearest 10.
Okay. Did you hear that? She said she added 30 12 times. There you go. There's the repeated addition, right? So she added 30 12 times. So she did 30 plus 30 plus 30 plus 30 12 times, right? And she also says right there that she rounded up to the nearest 10 just to make it easier on herself. And then what does she say?
So that was 30. I added that, I got 360.
360. So this gave her 360. So what she's just computed is she's just computed 12 times 30. 12 times 30. But that's too many, right? Isn't that what she says next? Go ahead.
I had to take away 12 because I had put one more to 29 to get to 30. So I had to take 12 away. And I took that away, and I got 348.
There we go. So she remembers that she added in an extra 12. Let me see if I can show that here. Yeah, so she computed this. I'm going to try to do it right here. Actually, give me a little more space here. So she did 30 plus 30. Actually, wait, I think I might have it backward. Might have to listen to this again. Dot, dot, dot. 30, 12 times, and then she got 360, right? But then she said that she had rounded 29 up to 30, so she's got an extra 12 in there. She's got an extra 12 in there, so what she had to do then was she had to subtract 12. Actually, maybe I'll say that. She had to subtract 12, and that's what gave her 348, and that's how she was able to solve it. And you can totally do that. You should do that. It's really amazing. Okay. And I can show you more examples of that later, actually. So we'll do that in the collaboration meeting if anybody wants me to do it more. I love it. It's really fun. All right, let's see who's next. Let's see how Nicholas does this problem here. 3rd grade, so a little bit younger.
Putting them on. Why don't you read what you did out loud?
I did 20 times 4 equals 80, and then 9 times 4 equals 36, and then 80 plus 36 equals 116.
Okay, so can you explain where those numbers came from that you used?
I got the 20 from the 29, I got the 9 from the 29, so and I knew that 20 times 4 equals 80, and I knew that 9 times 4 equals 36, and then I added 80 plus 36, which equals 116.
Okay.
Beautiful. Beautiful. Just amazing, right? Pause this here. Uh, Give me 1 second. I just lost my VLC. There we go. Nicholas. Nope, that's not it. There we go. Nicholas. Okay. Yeah, so that was another good one. So the question that he's being asked to answer is how many legs are on 29 elephants? I'm going to try to get it here. There you go. So legs on 29 elephants. So in other words, he's computing 29 times 4. That's what he's trying to compute. And rather than do it directly, he breaks it up using our number system, right? Our place value system. And he says, oh, look, I can do 20 times 4, which is equal to 80, and then 9 times 4, which is equal to 36. And then you can just add those up, and you get 116, right? 116, adding 30 plus 26. Or I'm sorry, adding 80 plus 36. Let's see if that's what he says at the end there.
Those numbers came from that you used?
I got the 20 from the 29, I got the 9 from the 29, and I knew that 20 times 4 equals 80, and I knew that 9 times 4 equals 36, and then I added 80 plus 36, which equals 116.
Okay.
Beautiful. Isn't that just amazing? Isn't that amazing? So again, this is why it's so important to understand our numeration system, because ease with these types of numbers, comfortability with these types of numbers depends on how comfortable they are with our numeration system. It's just really amazing. He knows what that 2 in the tens place means. It means there's 20 there. There's 20. Absolutely awesome. All right. Okay. Let's go to Thomas. Thomas, take it away. 5th grade.
I just drew 36 balls, and then I put 17, and it's like cotton. It's like cotton, yeah. I put like 17 cotton balls in each one of these, and 10 times 107 17 equals 170, and I just kept doing it 10, 10, 10, which equals 173 times. And then this one's a little different because it was 6 times. So what I did was take the 100, take the 7s and the 10s apart, and then 10 times 6 equals 60, and then 7 times 6 equals 42. 42 plus 60 equals 102, so that's what I got there. And then I added 173, those 370s, and then plus the 102, and then it came out to be 612.
Oof. Okay, did everybody get that? All good? Okay, next. Oh, no, I'm just kidding. Yeah, that one we have to kind of spend some time on and take a look at what he was doing. But what's amazing is that he was very confident and comfortable explaining precisely what he was thinking and precisely how to solve that problem to his classmates there. He's got no problem. He's just like, oh, yeah, I did it like this, and then I did it like this. He mentions cotton because they were using cotton balls earlier, and they were using cotton balls and talking about the partition method and like the array model and things like that. So he's even using what am I saying? Using manipulatives and other tools to model the operation itself. Just amazing, right? So he's trying to compute 36 times 17, but that's too hard to do, right? Can you do that without like an algorithm? No, at least I can't. So he starts splitting it up into meaningful chunks. Let's go back and see what he does.
I just drew 36 balls, and then I put 17, and it's like cotton. It's like cotton, yeah. I put like 17 cotton balls in each one of these, and 10 times 107 17 equals 170.
Okay, let's pause right there. So what he's saying is that he took 36 and he split it up and started thinking about it as 10 plus 10 plus 10 plus 6. He's obviously not writing this down in his head or anything, right? But as teachers, this is how we verify that that calculation is valid. So he says this, and then he's got times 17. And the 170 comes from him using the distributive property right here and distributing the 17 to those three tens. And that's why he says 170, because you're going to get 170 plus 170 plus 170, 70, and then you get plus 6 times 17, and he deals with that separately. So we'll come to that in a minute. All right, take it away, Thomas.
And I just kept doing it 10, 10, 10, which goes 173 times.
173 times. There it is right there. Okay.
And then this one's a little different because it was 6 times. So what I did was take the 100, take the 7s and the 10s apart, and then 10 times.
Okay, so let's pause here. Now he's focusing on this part in particular, and he says take the 7 and the 10 apart. So once again, he's doing the same thing. He's splitting up 17 into 10 and 7.
6 equals 60, and then 7 times 6 equals 42.
Yeah, so then 10 times 6 equals 60, and then 7 times 6 equals 42. This is actually one of those multiplication facts, as we call them, that students have to know. There's a certain amount of memorization in the early grades that is necessary. Multiplication tables are one of those things, multiplication and addition tables. Those are just exercises that students have to go through. They grind and grind, practice and practice and practice until they know those like the back of their hand. But even now, honestly, I still forget a lot of those ones. Once you get into like the 7 times 8, the 7 times 9, the 9 times 8, the 9 times 6, I get a little bit lost myself, but he's got it down, so that's good. But what's more important is that he even split up 6 times 17 to compute it more easily. And then he just adds the 2 up. He adds the 2 up right here.
42 plus 60 equals 102, so that's what I got there. And then I added 173, those 370s, and then plus the 102, and then it came out to be 612.
All right, and there's the conclusion. So now he says that he went through and he added 173 times right here. And then he added 102, and then ended up being 612 or something. I forget what he said right at the end. Let's see really quick.
612.
612, that's right. So that equals 612. So this is what we're talking about. This is the type of knowledge that we want our children to leave this grade having. It's just so powerful, right? He can do so much with this knowledge. He didn't even use an algorithm. He's not doing like the standard multiplication algorithm. He's just thinking about numbers and quantities and the things that would move around if you were operating on them. Awesome. Okay, so let's take a look at Amalinda.
What I did is I made the problem, and I put the 13 in the bottom, and I took away and I kept taking away, and I took away, and it left me to 13 remained the 12. 12 remained the 3.
Where did you get 12?
12. I kept on taking away, and I messed up earlier because I had 13 remained the 3, but I checked over and I made a mistake here because it had to be 107 and it was 120, and so I fixed it and I kept on taking away, and I had erased this and I kept on taking away, and I had 12. I counted these right here, how many times I took away, so I counted them, and it came up to 12, and the remainder was 3 because I couldn't add no more. Took away no more.
Beautiful. So she's using repeated subtraction, and what she's actually doing is what's called the expanded algorithm of division, and we'll talk about that in chapter 4, I believe. But she's trying to compute 159 divided by 13, and she's doing it by just repeatedly subtracting 13. Now, what I love here is that you notice that she's using that structure of the standard division algorithm, excuse me, that 13 bar 159. She's doing this, right? Standard setup. except she's just subtracting 13. So her work looks like this. And then she does it step by step. 146 minus 1 or minus 13 is 133, minus 13 is 120, and then she keeps going, right? And then what she says is she went back and counted how many times she subtracted 13, and the answer was 12. So that tells her that 159 divided by 13 is 12, and that's like the final answer right there. So there it is. It's just repeated subtraction. We'll talk a lot more about this algorithm in a later chapter, but I'll stop right there. Okay, let's see. Elaine is next.
I did 13 times 10 because, as we said like a couple of classes ago, that 10 is a landmark. So I did.
So Elaine kind of gave us her first step. Remember how when we did the how do I solve it, so we got the first step? This is one of the first steps, 13 times 10.
And I found out that that was 130 because, like, since it's a landmark, all you have to do is put this, since there's only 1 0, you just put it up here. So I found that out, and I just went put
130?
130, yep. And then I found out that I was 29 away from the right number, so I wanted to see how many 13s I could do. And then I
So
saw...
write that down, that you were 29 away?
Yeah.
So then you were, put it over here, 29 away.
Yeah.
So you wanted to see how many 13s would go into 29.
Yeah.
Okay.
So I knew that 13, I knew that 10 plus 10 was 20, and 13 only has 3 more than 10, so I did 10 plus 10, but then I just added a 3's into it, and I came up with 26, and then I added, because I knew that I was only 29, so I added 26 to 130, and I put the 6 here, and 3 and 2 is 5, and the 1 just stayed the same. So my answer was 156 remainder 3.
Was your answer 156 remainder 3? What was your answer?
Yeah, 156 remainder.
So if I were to put in this box 159 divided by 13, that would equal 156 remainder 3?
No,
No. What would it?
it would equal 12 because
There.
you're dividing, but I'm adding.
Oh, so here you were adding. Okay.
Yeah.
All right, so that's another interesting one. Again, she's using the same idea. She's using repeated subtraction, but she's actually looking at it from a multiplication perspective. What she did was she said, how many times does 13 go into 159? Well, she knows that 10 times 13, as in 13 10 times, that'll be 130. And that leaves her 29 units away from 159. So then she starts asking, how many times does 13 go into 29? And she realizes that you can get 2 more because 13 times 2 is 26. And then if you were to add these up, you'll get 156. And then now there's only 3 left, right? So she says that, this is actually what she says originally. She says 156 remainder 3. But what she really means is 12 remainder 3, because that's what's going on over here. Actually, let me use a pink highlight there. 12 remainder 3, because that's how many times the number 13 can fit into 159. 12 times, and then a remainder of 3. That's also why the teacher at the end kind of jumped in, because she was like, oh, wait a minute, do you mean 156 or do you mean 12? And what she said was she swooped in and she was like, oh, if I put a box right here, oh, sorry, oh yeah, if I put equals a box right here and write 156 remainder 3, is that correct? And the student was like, no, that's not right. So that's a really, really good way to get them to see what's the difference between a quotient, a divisor, a dividend, and so on. The other thing I wanted to point out is earlier on in the video, she has a moment where she starts relying solely on the symbols. You can see it right around here. She starts talking about, yeah, right around here. Let's see what she says.
Here. So I found this, since there's only 1 0, you just put it up here. Because, like, since it's a landmark, all you have to do is at, since there's only 1 0, you just put it up here. So I found that out, and I just went, put
130?
130, yep, and then I found.
Yeah, so she kind of starts referring to it there. It's not bad that she is relying on the symbols themselves because it can help give students guidance for how to organize their thoughts, but that's something to keep track of because you don't want students relying on those types of little tricks because once you get enough of those tricks in your bag, you stop actually learning about what you're actually doing, and it goes back to that mindset change that we talked about back in lecture 0, I think. Anyway, um, okay, so there's a couple more here. We're not going to watch the whole video of this next one. It's very long. We're just going to watch a couple minutes of it, but it's a good classroom interaction.
I think my strategy is too complicated because it's kind of.
Your strategy is too complicated, you think?
Because it's across division. He was doing.
Show me what you mean by across division, and let's see if you could
He
throw
was
that out
working
there.
on this between the two people we shared with. And
Yep.
Well, I set my problem this way.
This might be a good spot. Okay.
This is how I set my problem. And when I did 13 divided by 1,
Yep.
one was smaller, so I gotta go to the next number. I had to turn to the next number, so I did 13 times 13 divided by 15, so that is 1, and 13 times 1 is 13, and came up with 2, so I brought down the 9, and 13 divided by 29 is 2, and 13 times 2 is 26, and I did 9, 6, and I had the remainder of 3.
Okay. Now you felt this was very complicated. Can you tell me why you felt this was complicated?
Well, David said it was really complicated. I couldn't tell what it was just by looking at it.
You couldn't follow what his thinking was just by looking at it. Okay. Kevin, can you tell me when you were thinking?
Yeah, let me pause there for just a minute and let's talk about this for a second. So I think it's funny that it's like he kind of throws his friend under the bus. Oh, well, David said it was too hard, it was too complicated. But then David's like, no, 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 no. What I meant was I didn't understand what he was doing. I couldn't see what he was doing, which makes sense because it's hard to understand what he's doing because what he's doing is the standard division algorithm. And the standard division algorithm is very convoluted. And you'll listen, Kevin even says some things in this video that don't really make sense, but he writes the correct numbers down. So this is one of those times where this algorithm, again, it kind of divorces students from understanding what they're doing and just helps them get the right answer. And what's really cool is what the teacher does next. So let's keep watching.
Thinking about this, you said that 13 couldn't divide 1, right?
Because 1 was smaller.
1 was smaller. Okay. How did you know 13 could divide 15? I mean, you started moving over slowly, right? Is that what I see you doing? Okay. We haven't looked at this way of dividing yet, and this is a way that you have known how to divide before coming here, right? So this is a strategy that you use, but maybe you can help as we move through this to teach us how to do this strategy. So give us a little hint, something that you know that you think about when you do this.
Well, if 13 divided by 1, well, 13 times 1 is 13, and if 13 times 2 is 26.
Did you just know 13 times 2, or did you have a strategy to figure that out?
I just knew it.
That was one you just knew? Okay.
And 13 times anything can't go into 15.
Mm-hmm.
So I tried 13 times 1, and that's the closest, because if I try 13 times 2 is 26, that would be like too far away. And if I try 13 times 1, it's just two numbers close.
So in some cases, David, I'm going to show you something that I see in here that is similar to what you did. If we think, you step sideways a little bit, Kevin. If you see, a little bit more, like this. If you see in here, this 1, what place is that 1 in?
The tens.
The tens. Okay, let's compare this to yours. Here's a 10, So I see that if I put a 0 here, this shows your 13 times 10 right here. You see that? I just heard you do an oh yeah. And then you did some subtracting because he found what was left, what was the difference between here. Then he knew he found 2 more 13s, which is similar to your 13 here and your 13 here. So you both found 12 by taking the 159 and looking at it into 2 parts, almost. So there's some similarities. And this is a complicated way, and it is one way. We might not spend a lot of time talking about that way right now, but a lot of what we've done here connects with that. So I'm glad you did share that. Thanks, Kevin.
Yeah, so that's another really amazing one. So what she's doing is she's literally showing the connection between the repeated subtraction model that they were talking about in class and the standard division algorithm that this student was able to show the class how to do. So that's an important skill. You want to be able to pass between these different methods and show students that you can do that. Again, for what was his friend David? David didn't understand the standard algorithm, but he did understand the repeated subtraction algorithm, or the repeated subtraction model, and that's what was on the board on the left side over there, and that's what the previous students had done. Like who was it? Elaine, I think, and Amalinda, but that repeated subtraction process. Okay, so one last video. We're going to visit Thomas again. Thomas is going to show us how to do some division, and it's really impressive what he works out, actually.
What I did was I had 159, so I took away 10 out of that 159, and as soon as I got to 10, I knew that was 100 automatically. So I took away 10 out of out of the 50 and 159, and I minus 100 because I added these all together and there was 130. So I minus 159 minus 130, and it brought me to 29. So I gave each group 1 out of that 29, and I gave every group 13. So I minus 13 from 29, and that brought me to 16. And I gave every group 1 out of that 16, and I gave every group 13 again. So I minus 13 from 16. No, I minus 13 from 16, and it gave me 3. And I counted how much I gave every group, and I gave every group 12. So, and I had 3 left over, so my answer was 12 remainder 3.
Whoa, okay. So did everybody follow that one? No, that one's interesting. I'm going to try to reproduce his chart a little bit here, but he's using the sharing and partitioning method. He's not doing repeated subtraction. We can get a kind of a good look somewhere. So if you can see right there, what he's actually got is he's got a table, and in that table he has 13 columns, and he has them labeled. I'm not gonna draw all of them. He's trying to compute 159 divided by 13, and so he's got 1, 2, 3, 4, 5, and then 13 over here, right? And so what he realizes that what he's trying to do is he's trying to take 159 and divide it equally between 13 chutes, essentially, or 13 baskets. And so he starts taking numbers and just like assigning them to each, right? So the first thing he does is he gives 10 to every basket, right? And then once he's done that, he realizes that he's already assigned 130 things. So he kind of writes that off to the side. I don't have a lot of room, but he writes like 130 off to the side. That's a 30. There we go. No, it's kind of small. He writes that off to the side, and then he's like, okay, well, that's 130. I'm not sure exactly how many more I could fit. Then he just starts counting off ones, dealing out like single cards, for example. And then he says, okay, that's going to be another 13. And then he does it again, and that's going to be another 13. And then he adds these results up at the end, and he gets 156. And then he realizes that there's 3 left. And so what he does is he goes back and he looks at how many each column has in it, and it's 12. 10 plus 1 plus 1 is 12. So he says the answer is 12 remainder 3. Pretty impressive. And again, it just shows you the strength that this student has with our numeration system, and more importantly, just like numbers themselves. He knows what division is, he knows what multiplication is, he can explain it really well, It's really awesome. That's going to help him a lot as he gets older. Okay, so those are the last of the videos. Let me see, go back to the slides here. I think that's about it. Let's check here. Okay. Yep, that's it. So next is activity 3B. I can't remember if I pulled it up here or not. Let me check. 3A, I guess I haven't yet. Let me see if I can download this onto my iPad really quick, and we'll take a look at activity 3B. Sorry about that. Where are you? 3B. 3B. It's all about multiplication and division. There we go. Okay, multiplication and division. Usual instructions. Okay, so the first is just a question about our number system, essentially. So if you multiply a whole number by any fraction, will the result always be smaller? Prove your claim. So if you think it's true, show that it must be true. If you think that it's false, give me some counterexample that shows that it's not false. Here you're going to use the area model to demonstrate the distributive property with those specific numbers. And for this one, you can go back and refer to the slide about the distributive property and try to look at that particular representation of that property. That's what you're doing there. This is another question that shows that division doesn't always make smaller. So it says here, after years of working with division involving whole numbers, children often incorrectly deduce that division makes smaller, But that's not correct. Division doesn't always make smaller. So what you have to do is create a division word problem which shows that you're not going to end up with a smaller result by dividing. These ones are asking you to consider the context of sharing equally and repeated subtraction and just explain what those different parts are. Then you're going to use base 10 blocks to model 247 You're going to use base 10 blocks to model 247 divided by 6. Yeah, so you have to draw a picture that shows the necessary breaking apart of blocks. So that's one key thing about the base 10 blocks is you can't like draw a flat, for example, and then try to highlight some like portion of the flat. No, you can't do that. That's the whole point. The whole point with base 10 blocks is that they're chunked up. So what you need to do is you need to show the breaking apart of that flat into longs and then showing how you would separate those longs into the different baskets. That's the idea. And if you've got questions about that, please ask and I'll be happy to help. Very, very happy to help. And then I think that's it. Yeah, that's it. All right, so that's that for that activity. Let me see. Yeah. All right. So I guess that's it for today's lecture. Again, thank you for bearing with it. They'll be long and short sometimes, and I'll see you all in the collaboration meetings.